So our next speaker is Zhenghao Zhong, and he will tell us about Higgsing SCFTs, decay, and fission of magnetic quivers. Please.
Thank you very much for having me here. And today's work is in collaboration with Antoine Bourget and Marcus Spearling, and is based on these two papers. So what is the kind of theories I'm interested in? I want to do supersymmetric gauge theories or superconformal field theories with 8 supercharges. So these are 3d n equals 4, 4d n equals 2, 5d n equals 1, or 6d 1,0. But for today, I'll mainly be focusing on superconformal field theories, even though everything that I say can equally be applied to generic SUSY gauge theories with 8 supercharges as well. So these theories, they have hypermultiplets and vector multiplets, and it has a very nice and rich vacuum structure. So it's worthwhile to study the Higgs branch moduli spaces of vacua and the Coulomb branch moduli spaces of vacua. So this is the setting of what I want to do. Now the goal. So what I want is Higgsing SCFTs along the Higgs branch. So what do I mean by this? Well, this is really just the Higgs mechanism that we're all familiar with. You take electroweak theory, you have SU2 times U1, you give some VEV to the scalar fields, your Higgs boson. As a result, the gauge symmetry is broken to a U1. So I'm doing the same Higgs mechanism here, but rather than giving VEV to any scalar fields in the theory, I'm only giving VEV to the scalars that parameterizes the Higgs branch. Therefore, Higgsing SCFTs, but along the Higgs branch. So, given a theory T, I wish to find all possible daughter theories that it can Higgs to, and all the possible granddaughter theories that they can Higgs to, etc., etc., etc. Then I want to put everything together in a nice, beautiful phase diagram like this. And then it's mission complete. So, let's take a simple example. A 4D n equals 2 SCFT. So I have an SU3 gauge theory with 6 flavors. Now, what I have here is a quiver diagram. So basically, the circles represents the gauge groups, and the squares represents flavor groups. So just a nice and convenient way of representing my theory. And I'll be using quiver diagrams to represent my SUSY theory throughout this talk. So here we are, SU3 gauge theory with 6 flavors. Everything's nice. So let's do the Higgsing. So how do I do this? Well, I know what the gauge symmetry is. I know what the flavor symmetry is. So I can use some group theoretic methods, which is known for a long, long time. Basically, I just look at irreducible representations of the various fields in the theory and see if everything is consistent if I choose a symmetry breaking of the gauge group. So it turns out, doing this method, SU3 with 6 flavor can only be Higgs to SU2 with 4 flavors. So it cannot be Higgs to, say, U2 with 4 flavors or U1 with 4 flavors. Nope. Just SU2 with 4 flavors. Then I do another Higgsing, and I'll end up with a trivial theory, by which I mean just a bunch of free hydras. And that's it. This is exactly the kind of things that I want. A beautiful phase diagram showing all the Higgsings of SU3 with 6 flavor. Mission complete. But of course, in general, things are not so simple. The reason why everything works nicely here is because I have a beautiful Lagrangian description. I know what the gauge symmetry are, I know what the flavor symmetry are, but in general, for an SCFT, this is not true because I don't have a Lagrangian description. For example, let's take a 6D 1,0 theory. At low energy, everything's nice, I have a beautiful SUSY theory, but once I go to the UV superconformal fixed points, tensional strings come in, and I don't have a Lagrangian description anymore. 5D n equals 1, low energy, everything is nice, I have a SUSY gauge theory. Go to the UV superconformal fixed point, boom, bunch of massless instantons, I don't have a Lagrangian description anymore. 4D n equals 2, most theories we know in the literature that are 4D n equals 2 SCFTs don't currently have a Lagrangian description either. I don't have a Lagrangian description, I can't use this nice group theoretic method to do the Higgsings. Of course, there's other ways to do it, but it would be nice to have an all-encompassing way that works for any theory in 3, 4, 5, or 6 dimensions. So now we come into this little tool called a magnetic quiver. So this tool has been introduced for a few years now, and the idea of a magnetic quiver is that by definition, it encapsulates everything about the Higgs branch of all these 4D, 5D, or 6D theories, regardless of whether or not it has a Lagrangian description. So that's very nice. And once I have the magnetic quiver, I wish to perform what's called a decay and fission algorithm, and this is really the new focus of today's talk. And the idea is that using this decay and fission algorithm, I can now perform Higgsing on all these different SCFTs, even when it doesn't have a Lagrangian description. So, a brief recap of what is a magnetic quiver. So given a theory T, so right now T can be some superconformal field theory, but again in general it can just be some SUSY gauge theory with 8 supercharges. It can be in dimensions 3, 4, 5, and 6, and then the corresponding magnetic quiver is a 3D n equals 4 theory, such that the Higgs branch of this theory T is the Coulomb branch of this 3D n equals 4 magnetic quiver. So this is the definition. So now a few questions arises. Question 1, why is magnetic quivers always a 3-dimensional theory with n equals 4 supersymmetry? Well, that's because the Higgs branch, regardless of the dimension you're in, is always going to be a hyperkähler manifold. And the Coulomb branch, only in 3D for n equals 4 theories do I also have a hyperkähler manifold. So to compare apples with apples, magnetic quiver needs to live in 3D. So the second question is, why did I go through all this trouble to find this new little object? Well, the thing is, in the last decade or so, there's been many tools invented specifically to study 3D n equals 4 theories and their Coulomb branch. So now, once I have this magnetic quiver, it's really in my comfort zone. And I have so many different tools just to study the Coulomb branch of this theory, which is then equivalently studies the Higgs branch of T, even if it doesn't have a Lagrangian description. And finally, how do I obtain the magnetic quiver? Well, there's many different ways. And a preferred way in the literature is you first draw a brane setup, which describes the Higgs branch of T, and from the brane setup, there's a set of algorithms that extract such a magnetic quiver. Of course, I won't go into details in how to extract them. I'll mainly show you the results. So let's go back to our examples again. SU3 with 6 flavors. The magnetic quiver is given by this quiver gauge theory. So a bunch of unitary gauge groups connected. And just a recap, this means the Higgs branch of this 4D n equals 2 SCFT is the same as the Coulomb branch of this 3D n equals 4 magnetic quiver. And this also means that now that I have the magnetic quiver, I know everything about the Higgs branch of this theory. Now, back to the original question of Higgsing. Let's pretend I didn't do the group theoretic method before. So I don't know what SU3 with 6 flavor Higgses do. But the thing is, Higgsing, like I said, is just a movement along the Higgs branch. So I start with the big Higgs branch of SU3 with 6 flavors, and I move to a smaller Higgs branch within it. And that smaller Higgs branch is the Higgs branch of the Higgs theory, the question mark over here. But since the magnetic quiver contains all the information about the Higgs branch, there should be something that I can do to massage it into a quiver theory that describes the smaller Higgs branch. And indeed, there is. And this is the idea of the decay part of the algorithm. Basically, the algorithm says the magnetic quiver would decay into a smaller 3D n equals 4 quiver, such that the Coulomb branch of this thing is exactly the Higgs branch of the question mark. So I don't have time to show why this is the case, but it's actually quite obvious when you look at the brane setup for this. Okay, so now, because I have a quiver theory over here, I know everything about the Coulomb branch of the smaller quiver. That means equivalently, I know everything about the Higgs branch of the question mark. So now what I do is I go to the literature and I say, okay, which one of you 4D n equals 2 SCFTs has this Higgs branch? It sounds like a difficult thing to do, but in practice, it's actually quite easy to match them up. And this matches perfectly to SU2 with 4 flavors. So the first conjecture is SU3 with 6 flavors, Higgses to SU2 with 4 flavors. And then I do another decay. So this will decay to a trivial theory, which means SU2 is 4 flavor will Higgs to something with a trivial Higgs branch, and a conjecture it Higgs us to a bunch of free hypers. So this Higgsing tree, SU3 is 6 to SU2 is 4, Higgs to a trivial theory, is exactly what we got using the group theoretic method. Now, just by this example, may not seem that convincing. So let's look at some more interesting examples later on. But first, a quick understanding of why it's called a decay and fission algorithm. So basically, if you start with some theory T over here, and let's say this is the magnetic quiver, then the algorithm was take this magnetic quiver and decay it. So decay basically means I reduce the ranks of the gauge groups, so the numbers over here, in a way so that the resulting quiver is good, by some definition of what a good quiver is. So it tells me it decays to this quiver, and that means T will be Higgs to some theory T prime whose Higgs branch is described by this magnetic quiver. And now the algorithm says this quiver can decay in 2 different ways, to the left and to the right, and this means T prime has 2 different kinds of Higgsings, to T1 double prime and T2 double prime, and the Higgs branch of each is described by each of this quiver, and then we complete the rest of the diagram. We have a nice mathematical code to do all of this, so it generates the whole diagram in less than a second. It's nice and efficient. And the second part is the fission. So basically the magnetic quiver may go under a fission, which becomes a product of 2 magnetic quivers that are both good. And that means your SCFT will have a Higgsing into 2 decoupled SCFTs. Now this may seem, okay, makes sense, but what's the big deal? Well, this is actually quite subtle, and a lot of the Higgsings in the literature actually misses this kind of Higgsings that decouples the SCFTs. But it's clear from the magnetic quivers how this can happen. Okay, now let's talk about some SCFTs that doesn't have a known Lagrangian description. T4. Maybe it does, but then I can just choose another one. So T4 is a class S theory. It can be represented by a circle with a whole bunch of punctures. The magnetic quiver has been known for a very long time. So let's undergo decay. It decays to this magnetic quiver. Easily map it back to the SCFT in the literature. It's called the R0,4 SCFT. That's cool. I do another 2 decay to this one and to this one. And this means this will map a Higgs to a theory when you map it back to the E6 Minahan-Nanchansky theory. And the other one maps it back to the E7 Minahan-Nanchansky theory. Do another 2 decay. They all become trivial theories. So these 2 will be Higgs to a trivial theory. So this is a very nice example because class S theories will actually have a way of checking this, even though we don't have a Lagrangian. So this is called a partial Higgsing idea. So basically you partially close a puncture, and then one theory, well, you do a Higgsing by partially closing a puncture, and then the 2 results actually match together beautifully. So this is everything is consistent, but actually there's even partial closing of puncture doesn't describe all possible Higgsings for class S theory, but our algorithm does. And I just want to quickly go through, there's also Argyros-Douglas theories. So here's the Argyros-Douglas theory with the magnetic quiver. We can do all the different kind of decays, map it back to other Argyros-Douglas theories. Everything's nice and easy. And something funny happens over here. Basically, this Higgsing means I'm actually doing a Higgsing on the irregular puncture of the Argyros-Douglas theory when viewed in terms of class S, which, as far as I know, is not something that is done in the literature because I can't do this partial closure of puncture for irregular punctures. But in the magnetic quiver, this decay is very straightforward. You have the results before and after the Higgsing. Everything works well. And this is just the rest of the results. Not a big deal. And we can also look at theories that doesn't have a class S description, like this theory. It's called a rank 3 theory. So there's a symbol that labels the flavor symmetry. This is just a complex dimension of the Coulomb branch in 4D. So it doesn't have a class S description, but we have the magnetic quiver over here. Bam, here's all the different decays. There's even fission over here. And in this process, we actually found a new rank 3 SCFT that's not documented in the literature. That's cool. Another advantage of the algorithm. And the Higgs branch of this theory is described by this magnetic quiver. So that's fun. We can also do things in 5BN +1 SCFTs. So low energy, we have some SU5 gauge symmetry, 1 Chern-Simons level. for all flavors to antisymmetric. Go to the UV superconformal fixed points, boom, I don't know the Lagrange description anymore. That's fine. We know the magnetic quiver is over here. It's either decay to this theory, which is now labeled by a different 5D SCFT, or fission into these two 5D SCFTs. Easily compute the rest of the diagram, easily map it back to the original 5D SCFT. And you can then look at how many different families of known 5D and close to 1 SCFTs in the literature actually be Higgsed into each other. The black lines are more obvious, but the red lines that Higgs between different families are a bit more subtle, so that's quite interesting as well. So yeah, in the end we Higgs many different theories, 3, 4, 5, but also in 6 dimensions, like Orby-Instant-Hans, higher rank E-string theories, or little string theories. But we Higgsed a lot of stuff. Thank you.
Great, thank you very much. Are there any questions?
Can you say a bit more about the brain setup?
That was it basically. Can you talk a bit more about the brain setup? You said that from there it's easy to see how it works.
So from the brain setup, basically, I draw a brain setup that describes the Higgs branch of this theory. And then what's Higgsing in the brain setup? I take a dynamical brain, let's say a D3 brain in 3D, and then I send it to infinity. So that's its Higgsing. So what happens here is I take the rank of the gauge group, let's say it's rank K. If I send the D3 brain to infinity, it means rank K became K minus 1. So you just keep on doing that, and this is really just Higgsing. But sometimes when you reduce the rank by 1, there's a bunch of free hypers that goes along with it. So some of the other ranks of the gauge group start changing as well. So you can do the whole thing in a consistent way, and that's what the algorithm is about.
Yeah, so this was a very good talk actually. So I have 2 questions. So the first question is that can you make it clear that why do you even need Lagrange description to talk about the questions that you were talking about? For example, if I want to quote the fact that you can break SU2 to U1, you don't need Lagrange description to get this fact. So where does the Lagrange description come into play?
So well, when I do Higgsing, normally what I do is, for example, I look at the W bosons and scalar fields and different irreps they have. Let's say you have some gauge symmetry. And then I want to know that gauge symmetry breaks into various subgroups, but not all of them is possible because you also have flavor symmetries. So then I see which one is consistent by looking at the different irreps. So with the Lagrange description, I have the explicit gauge and flavor symmetry. This is easy. But in many of these SCFTs, when people found them, they just say, okay, all I know about this SCFT in 4D, for example, is like Coulomb branch operators, central charges, and the flavor symmetry. But just with these informations, in general, I cannot do Higgsings, at least not in the way that I said.
Okay, and second question that I want to ask is that did it ever happen that you Higgsed a theory and it went to a theory that's unknown? That's unknown in the literature. Okay.
This will be very often, and especially when you start looking at, like, let's say if you have a landscape of known SCFTs, but if you start with some SCFTs that you discover that's quite far away from the landscape, and you want to start doing Higgsings until you reach this landscape of known SCFTs, there's actually a lot of different things in between that is not known, but every single step, we know everything about the Higgs branch of those theories. So that is actually such a ridiculous amount of information, you can just start putting it in the dictionary, in the literature.
I see. So sorry, I have third question. So is there a specific reason that you are talking about theories that have 8 supercharges? It's because you had that condition and that's why you have theories in 3, 4, 5, and 6 dimensions. If you want to study theories in other dimensions, then you will need to change the number of supercharges, right? So is there a specific reason why you're using 8 supercharges only?
So because I want to study a theory with a Higgs branch, for one, so that is already quite constraining. And because only with that, I can find this magnetic quiver construction, which is by definition 8 supercharges. And when you look at the moduli spaces of theories with 8 supercharges, there's this beautiful stratification in the moduli space in terms of algebraic variety, and everything just works out nicely. But if you start going into other number of supercharges, a lot of issues starts arising.
Okay.
And this magnetic quiver description is no longer going to work.
Oh, it's not going to work.
Yeah, because it only works specifically for 8 supercharge. I mean, you may do something different, but I need to find an object to find a dual thing too.
Okay, thank you.
Thank you.
thank Zhenghao for the very nice talk. So I have a question. How are you sure that the theory you find that you think is not known is not known? For example, what do you know about it? You know the Higgs branch of the theory, but do you know something else about that theory, like the anomalies?
Yeah. Those are completely blind to me.
So, for example, there are non-trivials and n equal to SCFTs with trivial Higgs branch. So how do you know that the theory you obtain is not some known theory with these non-trivial theories?
So yeah, in these cases, so in some cases, the degeneracy can be lifted when we just look at the family of theories and see how the Higgs do. But in the cases, like you said, where like some Argyros-Douglas theories where there's completely no Higgs branch at the end of the flow, this is where the limitations of the algorithm appear.
Okay. Thank you.
Thank you.
We have time for another question. Okay, if not, let's thank the speaker again.